Take the numbers 2, 3, 5, 7, and 11. These are the indivisible atoms of mathematics. Every other whole number in existence is built simply by multiplying these primes together. If you look at this standard one-dimensional number line, you can see these prime numbers popping up along the sequence. The distance, or gap, between them is highly erratic. Sometimes they are clustered tight, like the gap of 1 between 2 and 3, or the twin primes 17 and 19. Other times you encounter massive, barren deserts with no primes at all. This diagram illustrates the consequence of that erratic spacing. It represents an analytic proof failure, a strict mathematical stall point where our ability to write a perfect unifying formula for primes completely breaks down. But that chaos we see might not belong to the primes themselves. The irregularity is an illusion created by the flat, restrictive one-dimensional space we force them to occupy. This side-by-side comparison shows how we escape that flat line. On the left is classical 1D space. On the right, we use Euler's identity, linking constants of growth and circularity as a rotational engine to map primes into a two-dimensional golden harmonics phase space. Instead of moving rigidly left to right, we plot numbers like targets on a radar screen. Every point requires two pieces of information, a radial distance from the center and an angle to sweep around the origin. Looking at this schematic, the purple box shows angular placement, dividing the prime by the irrational golden ratio, phi. This scatters targets pseudo-randomly, avoiding rigid clustering. The blue box shows distance. The radius is the reciprocal of the gap between consecutive primes. This inverse math creates a mechanical effect. A massive gap creates a tiny fraction, forcefully pulling the point inward to the center. Conversely, a tight gap of 2 yields a high value, aggressively pushing the point out to the far perimeter. This is the cartography of the primes map, showing what happens when thousands of numbers follow those two rules. A dense inner core emerges, formed by those rare, massive gaps, completely surrounded by a distinct outer ring of frequent small gaps. By running the numbers through this polar framework, the unpredictable spacing of integers resolves into an organized, symmetrical structure. This two-dimensional map is a diagnostic tool, exposing predictable rules of behavior that govern the entire prime sequence. This diagram shows a Markov chain transition mapping these rules. Notice the blue arrow reverting from a gap of 14 back down to 2. This illustrates a strict correction tendency, where large gaps frequently snap back to much smaller ones. If we take these complex polar coordinates and map them back into standard Cartesian space, those density regions align into distinct logarithmic spirals, directly governing how primes grow. This growth scale column demonstrates a phenomenon called a Fibonacci dimensionality split. Every time the sequence hits a Fibonacci milestone, like 5 or 13, the system resets its algebraic base, jumping from base 3 to base 6 and then base 12. These shifts in counting logic require more coordinate axes to distribute points evenly, forcing the 2D prime map to fold into 3D cubes and 4D hyperstructures. Primes function as a mathematical skeleton, a set of immutable anchors that allow this multidimensional routing geometry to converge. By shifting our perspective into the complex plane, we find that the perceived chaos of the number line is actually a one-dimensional projection of a much larger multidimensional symmetry.